Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. There are many great ideas in the broad machine learning community that can be specifically applied to time series problems. For this reason, the paper Boosted Embeddings for Time Series Forecasting caught my attention. I know firsthand boosting works great in a lot of applications, and I've been very impressed with embeddings for natural language processing. How well do boosted embeddings work for time series forecasting? Specifically with the deep GB approach? That's what I get into today with Sankarith Rao Karingula.
I'm Sankarith Rao Karingula. I work as a ML researcher at Palo Alto Networks, and prior to this, I finished my PhD from UC San Diego last year.
And is the work we're going to discuss today directly related to your PhD thesis, or were you studying other areas?
So during my PhD, I published on statistical learning theory and also published some theoretical work in theoretical computer science. But I use a lot of techniques from the statistical learning theory work I did in my current paper or in my current work at the company. So it's not a direct extension of my PhD work. It's the same kind of math, and I transfer the techniques from there.
Makes sense, yeah. Certainly the boosting techniques come out of statistical learning. We're going to talk about boosted embeddings and your paper Boosted Embeddings for Time Series Forecasting. But maybe to set the stage for listeners who have a passing familiarity, could you give a high-level definition of what boosting is?
So generally, boosting is a very general process. So there we have many weak learners. So you have many weak learners that can estimate some function with some probability, like let's say half plus epsilon. And now you want to put them all together. So each of these weak learners, they give you a weak estimate. And now you want to put them all together to come up with a strong learner. So the way you do it in a more general framework is like you keep successively fitting these weak learners and seeing on which inputs are they doing bad. And then when you query the next weak learner, you come up with a distribution such that the next weak learner would give informative predictions on the points where the previous weak learners gave wrong outputs. So you keep track of that and you are fitting the weak learners. And then you come up with a function of all of these weak learner outputs to be your strong learner, and that would have a very good accuracy as compared to any one of these. So this is a general model for boosting, but in a specific framework, you just fit sequence of trees, like decision trees, one after the other, like in a standard gradient boosting framework. You calculate the residual, and every time you fit a gradient tree, a decision tree, and then you calculate the residual, and on the residual, you'll fit another decision tree, and you keep iterating until you come up within some required threshold of error that you want.
Well, I'm going to guess that most listeners are already familiar with gradient boosted trees and the famous XGBoost algorithm. Very popular and for good reason. It's really powerful, sets a lot of benchmarks on many broad domains. But time series can be something specific, and it's not obvious to me that boosting is going to work well in a specific time series domain. What were some of the inspirations that thought this would be a fruitful path to explore?
So the techniques that we give are these are before the boosted. So we give these embeddings that will give you before you put an XGBoost on your time series. The idea is that we have many categorical variables. Let's say there are different additional categorical information that you have about your time series, and you're trying to remove each of these categorical variables that gives some information about your time series. So you're trying to successively remove on each of them. You're trying to first remove categorical variable, what information does it provide? Let me try to remove that. And then let me try to remove the additional information from this next categorical variable. And then let me try to get rid of all of these correlated information that I'm getting from these. And then I have a pure time series problem on which I can apply other techniques to it. So this process is naturally boosting fit into this natural framework where you're successively removing the effect of each of these. First you remove the first categorical variable, and then you see what more can you remove from the second categorical variable. So for us, it came like a natural approach to look for boosting approach to this. And once we remove all of the effects of all the categorical variables, then we apply any general model that you want to fit. So this iterative process of calculating the residual and fitting different models, this naturally fits in the boosting framework. So that was the reason we were looking for this.
Well, what specifically is a boosted embedding? I know about boosting and I know a little bit about embeddings. How do you bring the two together?
So I can first explain why these embeddings are important or why it's useful. Let's look at the classical time series forecasting techniques. So first we have like ARIMA or like regressive integrated moving average techniques, or like SURIMAX, or like seasonal ARIMA plus exogenous variables, or we have these different techniques. And then there the issue is when we analyze their performance. So when we look at ARIMA, there are like two components. There is a seasonal component, like you sample the series at large intervals of time, then you see that adds into the seasonal component of your ARIMA model. Whereas there is a local small window over which you'll do a forecast, the local PQD parameters. But then the issue is that to calculate the seasonal parameters, you need to look at really long windows. And we try to avoid that. So how can we come up with other models that will get rid of this seasonal thing so that you can just look at small windows or like simple models that already have the seasonal part of your data taken care of? So that's where we were trying to understand like how to come up with better things than looking at the big broad windows. So that's where we try to fit like different embeddings. So you have the time categorical data, like which day of the week is it? Is it a holiday, or is it a specific well-known day where there is a huge traffic? Like we have all this categorical data, so we try to use that to come up with this seasonal component of your data, so to remove the seasonal part of your data. And surprisingly these performed really well. And in terms of like there were other well-known techniques, like Facebook has this tool called FB Prophet, like, and they have followed it by Neural Prophet. So there what they do is to calculate the seasonal components, they look at the Fourier transform of your signals. If you have your time series in your time domain and you look at it in the Fourier domain, you'll get all the, if you calculate the different Fourier components, they'll calculate like the different frequency components of your signal. So using that, they'll calculate the seasonality of your signal and try to remove the seasonal component. But then most of these techniques, the issue is with ARIMA, you need to look at really big windows. And with FB Prophet, like you calculate the Fourier transform. But then if there is some holiday or there is some, I think they can handle holidays, but if there are some aberrations to the seasonality, it would really affect their techniques. So we try to come up with something that's robust and that also captures this seasonal components of your time series. So that is where this embeddings came in. So now we have embeddings for different categories, and how do we combine them together? So this is where we have this technique. So the natural way is to calculate the embeddings and then subtract out the previous embeddings, and then take one categorical variable, take its embedding, remove it, and then fit the next categorical variable, calculate its embedding, remove it from your time series. And so this naturally fit into the boosted framework. But we have a slightly different trick where we have sequence of like we construct these embeddings one after the other, but we freeze the weights of these embeddings. So we use the Keras embedding layers and we freeze their weights. And when we successively put the next variable, next categorical variable, we freeze the weights of the previous variable and then iteratively build the whole network and then calculate the residue and then fit a different models.
Well, we've been talking about and describing some of the inner functionality without naming the algorithm, the deep GB algorithm. I was wondering, could you give the elevator pitch for it? If there's a listener who has a new greenfield time series problem, they're considering Facebook Prophet, maybe they've heard something about seek-to-seek models, there's so many options. What's the pitch for picking up deep GB?
So you want something robust and you want something which will allow you to fit any model that you want on it. Like we will just compute the embeddings for you. We'll remove the embeddings from your time series. And after that, you can fit any model that you want. You can fit CatBoost, you can fit XGBoost, or you can fit ARIMA or whatever model that you want. We will do the embeddings process for you. And we are very robust and we are very, as compared to seek, we perform much faster. And it captures more complicated relations, nonlinear complicated relations, temporal relations in the time series that are still captured by the embedding, like the seasonal or the categorical data. We remove all of these components for you and we'll give you the resultant time series on which you can fit it with any other model in a modular way. So that's the main reason why we would propose this as DeepGB as a good tool in your arsenal, which can be used with any other model that you want, and how it's a better approach than FB Prophet or Seek to Seek or like other approaches that are currently available.
So I know from experience that one of the, I don't know if I want to call it a weaknesses, but just an observation about ARIMA is that it works best when things are a little bit regular. So I was working in a scenario where we were trying to study the impacts of promotional events like coupons and these things like that. And they were regular. We would kind of do them like first Friday of the month, that kind of stuff. But of course, the first Friday shifts around with a high variance. So we struggled a little bit to get the methods to work way back when. We didn't have deep GB then. In a scenario like that, where things are seasonal but with, some fluctuations or maybe some exogenous variables at play, how does deep GB approach the problem?
DeepGB would be the perfect tool for this. So you have some seasonal component, but it's not exactly seasonal. There's some aberrations, or DeepGB would be the perfect fit because you look at all the other covariating categorical variables, right, that vary with your time series. So DeepGB takes into account all of these covariating series and calculates like the right amount of things to remove so that these effects of this variation in this seasonal kind of component goes away. And once that is done, you can fit any simple model, even ARIMA would work. So these nonlinear, like slightly aberrant seasonal components are exactly what DeepGB would remove. And the way we go about it is we look at all the different data that you have and calculate how each of them captures some information that is about the whole time series and keep removing them successively. One other thing is after that, you can use anything. Like if you use ARIMA with a small window, like if you directly fit an ARIMA with small window, don't use any seasonality, then your errors will really blow up. So usually you need to remove the seasonal component in ARIMA. So we simplify that for you. And after that, you can fit a small window ARIMA. So that will be very, very fast for you.
Well, let's dive into some empirical results. How does DeepGB stack up against other techniques on common data sets?
First thing, in terms of time, ARIMA is really fast. But then in terms of time as compared to like seek to seek, DeepGB performed much better. And we were looking at like some company data sets. We had some networking data, and we also looked at Wikipedia data on like that. We had access to Wikipedia data sets, and we looked at both the time and the accuracy. In terms of accuracy, the DeepGB was really good. And we had to use some residual model. So what we used was a CAD boost, like 800 trees with of depth 3. This is the residual model that we use, but you can fit any model that you want after we remove the boosted embeddings. So that's the model we used in the experiment. We compared it with seek-to-seek, and we compared it with other like standard ARIMA, and for ARIMA we just used the stat models ARIMA, and we noticed that our technique was much faster than the other deep learning techniques, and it was much better in performance than even the classical techniques. Even if ARIMA was faster, we did much better performance. So in terms of both the things like performance and time, if you want the best technique, this would be a very good fit. And not only is this a good fit, you can also fit any model that you want. So we are just helping you fit any model that you want. We'll just take care of this nonlinear seasonal, these kind of components. And then you can replace our CAD boost. CAD boost was just one off-the-shelf thing that we use, but you can replace any model that you want. And if you think your model is performing good, then just apply boosted embeddings and then fit your model. You'll get even better performance. So that's the kind of thing we are offering, like a modular thing to fit in first before you fit in your model, any model that you want.
Today, many small business owners are busier than ever. Time spent searching for and interviewing candidates can take time away from managing and growing a business. That's why LinkedIn Jobs has made it easier to get to the candidates worth interviewing faster, and it's free. I have hired a number of senior professionals in my life from LinkedIn Jobs specifically. Everyone's there. Go drink from the fountain directly. Create a free job post in minutes on LinkedIn Jobs to reach your network and beyond to the world's largest professional network of over 770 million people. Focus on the candidates with the skills and experience you need. Use screening questions to get your role in front of only the most qualified people. Then use simple tools on LinkedIn Jobs to quickly filter and prioritize who you'd like to interview and hire. It's why small businesses rate LinkedIn Jobs #1 in delivering quality hires versus the leading competitors. LinkedIn Jobs helps you find the candidates worth interviewing faster. Did you know every week nearly 40 million job seekers visit LinkedIn? Post your job for free at linkedin.com/dataskeptic. That's linkedin.com/dataskeptic to post your job for free. Terms and conditions apply. Seamless ML. Are you a data scientist? Kegler, physicist, mathematician who wants to be a data scientist, or quantitative researcher, Seamless ML is looking for exceptional people to join their team. The team is already stacked with one of the best poker players in Europe, one of the best cosmologists of his generation, and a top 20 Sudoku player in the world. Seamless ML is applying machine learning to do algorithmic trading. That's a challenging but incredibly rewarding project. If you're deeply committed to excellence in machine learning, this team could be the place for you to leverage your training and take the next step in your career. To learn more, head over to seamlessml.com/jobs. That's seamless, SEAMLESS, ml.com/jobs. My first exposure to embeddings in general goes back to Word2Vec. And, there's been a kind of natural progression up to things like Elmo and BERT that we've covered extensively on the show. And it seems like in a lot of cases for natural language processing problems where those two things apply, it's just sort of common practice nowadays. You embed your data to begin with, and then you work off the embedding space for everything forward. Do you imagine the same sort of progression now happening in time series, that there will be DeepGB or maybe a family of algorithms like it that are just common pre-processing steps?
Oh, yes. There is already this algorithm called time-to-vec. Like when we re-implemented seek-to-seek, we actually use time-to-vec. So time-to-vec is an analog of Word2Vec for time series. So most of the techniques from like NLP, you can translate them. Like even seek-to-seek was first developed for like NLP, right? So you can translate most of these techniques. And the analog for Word2Vec would be the time-to-vec model. And that we already used in our experimentation. And yes, that's what we are shooting for. So we want boosted embeddings where, like, when you have many different categorical variables and you want to get rid of all of their effects, there's a lot of information, right? Whenever you have some use case, like for instance, we had to do like a memory leaks use case in our company. The team just came to us like, oh, we have this 18 different processors when we have like this tons of data. So can you detect when would memory leaks happen? So we had all of these like other exogenous variables, other time categorical variables, and there were like so much extra data. So there, like in such problems, we would help you come up with like nice ways to remove these external categorical data's information about your time series. So that's where it would be very useful. And I would totally see it as a successive, like first do time-to-vec on your time series column, and then use our DeepGB framework to remove all the categorical embeddings from your time series. And then you will have a nice time series. Then you can nicely fit any model that you want. So usually that's what we're shooting for. That's exactly what you said. So yeah, that's the kind of thing we're shooting for.
When I review the empirical results from the paper and the various data sets, DeepGB wins in a lot of contests. Not every data set, but it's certainly a contender all the way down, which makes me wonder, is there a cost to be paid here? Do we get this advantage in reducing error, but we pay it computationally, or it doesn't scale here? What are some considerations for how the algorithm will stack up in those regards?
It's deep neural networks. So we are using like the Keras embeddings, and we are using like deep neural networks. So you suffer in terms of like the performance cost, like in terms of like with respect to ARIMA, like ARIMA would be super fast. We would be slower than ARIMA. But so if you look at the times, like if you look at my paper in the training time, let's look at this data set, any data set that you want to pick. Like in terms of training time, the ARIMA is super fast. So it's like if you look at this Wikipedia 2NEZH, ARIMA was just like 0.22 seconds, but ours took like 5.86 seconds. But whereas compared to other deep learning models, it's still like 3 times as faster. Seek-to-seek with time-to-vec and everything included when we re-implemented, it was like 17 seconds. So we are paying in terms of time as compared to other statistical, like classical ARIMA kind of methods, but then we do much better job in terms of the error. So if you are paying the price to use a deep neural network and pay the price in terms of like time, training time, then this would be a very good fit for you in terms of like the accuracy and the modular nature of it. That's the price you pay, but that you pay with any deep learning technique that you use.
Well, broadly speaking, those deep learning techniques are starving for data. They need lots and lots of input. Although the two I'd mentioned earlier, Word2Vec and the BERT model, are, a pre-trained model. So I could download BERT, and even if I have a small corpus of NLP text, I already get, these powerful embeddings I can use. And maybe a little out of scope for the initial work in this paper, but do you see an opportunity there? Could there be some sort of economically pre-trained model or retail-based, some sort of industry-based pre-trainings that someone using DeepGB could take advantage of if their time series data was a little bit smaller than they'd like?
We were thinking about more like allowing the user to train their own networks and train their own embeddings. Like the main issue I'm thinking of is like in language models or these, we have these words, like if you say a bird, it's still a bird. I mean, if you have a huge amount of information, you can train these pre-trained models and you can deploy them. And I'm not able to find a similar framework in time series because every time series could be totally different. It could mean different things, and it's just real numbers as opposed to like I don't see some global I'm not able to think of any global interpretation for or like if there is some common pieces like in these bird kind of models that you can fit. So maybe the parameters of what length to use based on what, like for instance in ARIMA, when you're doing autoregressive techniques, let's say I can tell you which PQD to use based on which kind of time series you have, such kind of hyperparameters or these things I can give you, but I do not see a natural translation from like models like BERT for time series framework. Maybe there are, I need to research this more, but I'm not able to come up with something.
But you raised some excellent points. I mean, language is language. We use different words, but we're all trying to do the same sort of thing. Whereas if I have data about, bird populations and you have data about the lumber industry, it's not necessarily going to correlate in any useful way.
Some things I can tell you is like if its variance is this much, or like based on those, I can tell you hyperparameters. Okay, you fit an ARIMA, I won't tell you which coefficients you'll use in your ARIMA, but I'll tell you what window length do you need to use, what moving average parameter Q do you need to use, what like regressive P parameter can you use, or like how many times do you need to differentiate to get to stationarity, or things like these I can maybe tell you, but the exact coefficients or like giving you a pre-trained model that you can fit with any time series without any training, I wouldn't imagine. But we were working more in terms of giving you the model and letting you train with it.
To, I guess, follow up on that, do you have a sense of how much data someone needs in order for this method to be the right choice for them?
Usually we work with like, it depends on the window length primarily. We don't have any hard restriction for it to work. So in terms of like, you calculate your right window length and whenever you have a big, huge time series, let's say, and you calculate like we use like in our work, usually empirically, it's like if you want a forecast for like X days, you need to use a window length of 2X days. We work with that assumption, but then you take your time series data, you sample it at some points, like you get some discrete time steps at which you get it, and then you batch your data, like you create like these window batches, and then based on your window length, you can make the next prediction. And then now you train your model, you create a tensor from these windows, like you have many windows and you create batches, and then you create your tensor and you train it. So as long as you have sufficiently enough, not very large, like some 1,000 data points, or that would be enough for like a 60 look back window to get a prediction for like 10 points ahead, or would be really, really accurate with this technique that we are using.
Well, I think DeepGB, the paper describes it as a great achievement, but it also opens up a lot of opportunities for other interesting lines of research. Where do you see this line of thought going next?
Oh, yes, there is a lot of nice research. So one thing we did not explore, we are currently exploring is like which order. There could be like, there are many categorical variables, right? That you can get. Not only do you observe your data, but you observe many different covariant categorical variables and other exogenous variables. So there is like the order in which you'll remove the embeddings was very important to us. So we fixed an order in the paper, but we wanted to study it more and empirically come up with like, intuitively, we believe like if you have heavily varying time series, covariant time series, or like other categorical data, then you don't remove that embedding first. You remove like a slowly varying thing, and that itself might remove the effect from the other exogenous variables. So, and then you iteratively go in that particular order. So this was one research direction we are currently pursuing. And this opens up like you can use this as a module and you can fit any new model. Now that you have the seasonal component is getting taken care of, you can fit any of new latest models to this and try to come up with better and better models and beat the classical methods. Even with ARIMA, we were trying to change it to like IBE ARMA kind of technique. So we first integrate, and integration step we do first in terms of like we'll differentiate your time series to make it stationary, then we'll fit our embeddings, and then we'll fit ARMA techniques and see how it's performing. And in terms of any of these different classical techniques as well, you can tweak them with these embeddings, put them in that and see how the performance is improving. So there's a lot of nice ways this can be used in any of the research that you're doing. So that's our main selling point. Rather than give you one specific model, we are giving you a technique that can be used with any other technique that you want to use. We'll just take care of the like the seasonal kind of object, and then you can fit any model that you want. And like there's a lot of active research we are doing at our company, like in terms of like there are nice forecasting techniques. Have you come across deep AR? Like Amazon has this deep AR technique, which is really good. So they have this LSTM model, and then they iteratively sample from there. Like they make a prediction, and then based on it they'll make the next prediction, and based on that they have a state vector that's passing, and then they do these predictions. So we are trying to see how we can use such techniques and trying to play around with all of these and trying to come up with better and better forecasting techniques based on all the deep learning and new models and all of the latest research that's happening. We haven't implemented transformers yet, but we are looking at that direction as well in the company, and there's so much active research that's going on. It's a wonderful area to be in right now.
Well, one of the things that also struck me about the paper is it kind of has a foot in both worlds. It's a deep learning approach, but is embroiled in the classical techniques as well. This isn't always true. If you think of a stereotype of deep learning, it's forget you, grandfather, we're going to do everything from scratch, we don't need any methods, we're going to learn it from first principles. Do you think this is more of a trend that we'll start to see this hybrid approach becoming more popular?
I strongly believe that there are a lot of knowledge already there, right? And you need to beat those benchmarks and you need to append to those techniques and improve it rather than just throwing it off and then trying to rebuild everything from scratch. For instance, the error metrics, right? How do you calculate the error? So do we use SMAP, or like if we use SMAP, like how do you take care of the zeros or things like that? There's a lot of nice work that's already been done, so we can learn a lot. So for instance, like you actually hosted Hindman on the series, right? So he's one of our like team actually refers to all his work in the forecasting techniques. And there's like one of the books I really love is De Prado, Advances in Financial Machine Learning. So he has a very good research on like for time series forecasting, like how to handle your data, benchmarking, and all of this backtesting and all of these techniques for in the classical framework. So we try to inculcate as much as we can from there and then try to see what can deep learning give in advance to this. I feel that's the right approach rather than throwing everything off, and then because then if it doesn't work, then you won't know what to do. Like if you're building it you're understanding the pieces and you're putting them together, even if you're using deep learning, that would be a much better research approach, because if things don't work, you know which piece to remove and what to replace or why it's not working, and then you keep building better and better models. So I definitely believe that's the way to go. Like using all the classical knowledge, try to understand which piece needs slight improvement and how can deep learning help, and then fit that with that and then progress ahead. That's the best approach, I believe.
Well, before I go into a wrap-up, is there anything you think we should have covered that I didn't get to?
Just one thing is in terms of the application. So there is like right now forecasting is like in terms of like the business connections. I'm seeing there was some recent power energy forecasting startup that I was seeing where they were trying to forecast, like use these techniques for energy forecast. Like, and then like Amazon has deep AR, they use it for all their like inventory data that they're doing. So in terms of that, I would feel like forecasting is a very, very important problem. So I just wanted to say that.
Absolutely. Good advice. Where can people follow you online?
You can add me on LinkedIn and I have my Twitter page, and we'd be very happy to chat and talk about our latest work.
Sounds good. I neglected to ask. I read your paper originally on Archive, but tell me a little bit about the conference it's going to appear in.
We published it in like the Machine Learning, Optimization and Data Science Conference. So this will be held in October 4th to 8th in London, England, UK. So you're free to attend the conference, and there's like a lot of nice machine learning techniques that are being presented there, even from industry and academia. So feel free to tune in and listen to our talk, and would be happy to connect and about the kind of work we are doing.
Sounds good. Well, I'll have links to all that in the show notes. Thank you so much for taking the time to come on the show and share your work.
Thank you so much, Kyle.
That concludes another installment of Data Skeptic Time Series. Our guests today, Sankarith Rao Karangula. Thanks to our sponsors, LinkedIn and Seamless ML. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, and our host, Kyle Polich.